Hope you can hear me, and hope you all had lunch and caffeinated. And let's get started. My name is Chen Wang. I'm a solution architect from AI21 Labs. So today I would love to share with you about how to train a large language model with a novel architecture we developed at AI21 Labs. And yeah, no matter what you do with LLM these days, hopefully, peer under the hood of how to train LLM will be an interesting topic for you. Awesome. So just a little bit of level setting. So about 3 months ago, we released our open sourced foundational model, Jamba, on Hugging Face. And very soon after that, the model actually topped the Hugging Face leaderboard chart on #1 for a while. So really exciting for us. And also because the model had a hybrid SSM state space model, which is a sequential model hybrid with Transformer, which is very novel. And we'll talk a little bit more about it today. And it also caught a lot of attention in both academia and industry as well. About a month ago, our aligned version of the model, Jamba Instruct, also came to our SaaS. And yeah, so everyone can use it today, actually. And also the Jamba model is coming to, sorry, the transcript is blocking a little bit, but the model is also coming to Databricks on Marketplace and external model serving as well. A little bit overview of agenda today. So first, I'll just very briefly share a little bit more about our company, AI21 Labs, so you know who we are. And I'm very aware that the ones and L's and I's in that logo is very confusing. And trust me, Robbie and I, we've heard all the different versions of it, so you won't be the first. And then we'll spend most of the time today talking about our model, Jamba model, Transformer, and the Mamba architecture hybrid, and also the advantages coming from it, and also how to actually train it. And if we have time, I'm not entirely sure, we will talk a little more about compound AI systems, which is something Matej mentioned yesterday and also this morning. If you heard from keynote, there's a lot mentioning around similar school of thoughts. We will also share our approach as well. Yeah, just about our company. So the company was founded in 2017, mostly as the NLP and machine learning research lab by 3 co-founders, Professor Amnon Shashua, Professor Yoav Shoham, and Ori Goshen, and they all had amazing track record. For example, Professor Yoav was a professor at Stanford for 37 years, was the director of their AI labs for a very long time. And the company started by developing a B2C application called WordTune. It's a reading and writing assistant app, accumulated around above 10 million users over the time. And we also developed all these specialized language models supporting this application, of course. And at this very moment, the company is really focusing on developing enterprise-ready AI systems, especially using relatively smaller AI models. That's that. OK, so just level set. I'm sure everybody already super familiar with LLMs. If you didn't go hibernating for the last 2 years, we all know how this works. Pretty straightforward. So the large language model, it takes in a string as an input and then tokenize it into smaller chunks. And by the way, every different large language model have different way of tokenizing words. So if you feed into different LLMs, it actually will, the same word can potentially be sliced and diced in different ways. And then the LLMs takes the token and token input and generates the next token, right? And then it does it iteratively. And that is essentially what you get from interacting with a LLM chat application like ChatGPT. But actually, this idea is not new, right? A lot of the core ideas can be traced back to a couple of decades ago, and some may even argue like a century ago, a lot of the core idea of RNN has already been developed in the 1920s. And so what really changed? Everything really caught the eye of public around 2022 when ChatGPT was first released. And between all this time, I think we can all kind of agree on there are 2 very important things really happened. One is the explosion of internet data. So now LLM has a ton of data to learn from. And second thing is the improvement of hardware, right? The GPU performance has really improved to enable training larger and larger models. So as you can see here, the model size since 2017, the Transformer paper came out, the model size has roughly increased 15,000 times. And if you look really closely to this plot, you can actually also see an overplot of NVIDIA stock price here. And no, I'm kidding. NVIDIA actually did much better than this. OK, talking about transformers. So before 2017, right, before Attention is All You Need paper came out, the NLP field is dominated by, let's say, RNNs, recurrent neural networks. There are sequential models. It actually makes a lot of sense, right, because language is a sequence. So you want to use a sequential model to model it. But there is a big problem with sequential model, which is that early days, the sequential model has to be computed in a sequential way, of course. So it's not very parallelizable to leverage GPUs. So that's the problem Transformer solved. And so at 2017, the Attention is All You Need paper solved this problem by doing self-attention mechanism. So instead of doing everything sequentially, now we're looking at token-to-token relationship, so everything can be parallelized and leverage GPU very, very efficiently. And as the field develops, since then, our company also founded at 2017, and since then, released WordTwin app we talked about earlier, and also our foundation model, Jurassic family of models. And fast forward to 2023, right? As we all are using LLMs more and more, especially with long context windows, the compute inefficiency has been catching up for transformer models, right? If you're running a pure transformer model, the model is basically, in training, they have to calculate width for each token in relation with every other token. Right? If you have longer context window, the compute scales up quadratically in training and linearly in inferencing. Right? And that is very, very expensive, both for training and for inferencing. By the way, for inferencing basically means when you're using the LLM. So that means lower response time, very expensive compute, and high cost for users. And that's the exact problem the Mamba paper was trying to address. So Mamba paper was published December 2023, about 7 months ago. And you know how they did it? Guess what? They're also, the Mamba paper is actually also a sequential model, similar to RN in many ways, you can say. But this time, the difference is that it actually, the two authors did a lot of great work to actually be able to parallelize the compute for training the Mamba model. So now you have sequential model, but also can leverage GPU very efficiently to scale it up, right? So now with the Mamba architecture, the training compute only scales linearly to the context versus quadratically for transformer. And also the inferencing time is going to be constant versus linearly scaling up with transformers. But there's also a problem with Mamba. So initial paper using pure Mamba architecture, the model stability and the performance will degrade above around 3 billion parameters. That's how big the author tested. So that's why the paper caught our attention, and we tried to hybrid blending the Mamba architecture with transformer architecture to build our Jamba model, which kind of blending the best of two worlds to have this model that is both very high performing and able to scale up to 52 billion parameters and also super efficient. This is sort of just an overview, simplify what we just said. So by blending transformer and Mamba architecture, by the way, Mamba architecture is this sequential model we just talked about. The Jamba model was able to have very high quality output, very high throughput, also very efficient, low memory footprint, get the best of both worlds. Oh, oh, okay. Did I skip it? No. Awesome. So a little bit more details about the actual model architecture. So the model has about a total of 32 layers, and just to easily explaining everything, we can divide the 32 layers into 4 Jamba blocks, and each block has 8 layers. And among 8 layers, there's 1 layer of transformer. We added in transformer just because pure Mamba architecture doesn't scale very well when you have a larger model. And we also have 3 pure Mamba layer and also 3 Mamba plus MOE layer. MOE is mixture of experts. A lot of you may know. Just in case you haven't heard about this, a mixture of experts is basically a type of architecture where you divide your network into different experts, right? So during inferencing, not all the experts are going to be activated at the same time. So it's, again, a way to increase efficiency in inferencing stage. Really, the point I want to get across is that the team did a really good job of combining a lot of significant advancement in LLM field in the past couple of years, including attention related to transformer and mixed experts, and also Mamba to have a really good model that also scales really well. Another very interesting way to look at model size, actually, this is, I think, very interesting slides, which if you think about if you say, hey, how big is this model today? The number one thing came to our mind is the number of parameters. But that is relatively simple, straightforward for a vanilla or pure transformer model because all the parameters in your LLM will all be activated during inferencing, right? So that's true for some of the models there, Mistral and Llama. And when you're adding MOE, mixture of experts architecture, that's not true anymore, right? So the model can have a much larger number of available parameters in total, but only part of the parameters part of network are being activated at every time during inferencing. So the active parameter is actually a lot lower. So you're able to achieve equivalent results with a lot more efficient model. And with the Mamba architecture, as we talked about earlier, because Mamba architecture actually doesn't, if you have pure Mamba, it actually doesn't really have a scalable cache memory when you're doing inferencing. So it's super, super efficient in memory. And in the Jamba model here we're listing, the KV cache, the key value cache memory, is actually mostly coming from the transformer layer we added in there. That's why roughly it's an eighth of mixture model, which is around the same size. So it's super efficient. Again, kind of want to address the same point here. And also because the low cache value, the low cache memory requirement, the model is able to handle a lot longer context window, which is super important for many use cases these days. For example, long doc summarization, or if you have a long call transcript, whether it's call center or interview transcript, whatever that might be, the information can be scattered around in your transcript. Doing a RAG may not really solve your problem, and having long context window can be pretty helpful for those cases as well. Awesome. So I think we kind of covered, for now, a brief overview about what is Jamba, what is the model we're doing, and how did we what's the thinking process there. And so how do you actually train it, right? So this is actually a very high-level generic view about how to train an LLM. You can see bottom there, but basically says picking and crafting the right model architecture. And then you train the model in the pre-training stage with trillions of tokens. After pre-training, right, there's a step called alignment. And alignment basically means that, so after pre-training, the base model is gonna do one thing really well, is predicting next token, right? But alignment stage is really a stage where we try to encode our preferences, human value, human goals, and human preferences into the LLM. so that LLM does what we want them to do instead of just predicting whatever it learned from the pre-training data set. So in alignment, typically there's a lot of different tasks we want the model to excel at, including instruction following, chat, math, reasoning, logic, coding, whatever that might be. And on top of that, safety and security guardrails are super important, right? We all know that we want the model to be able to avoid making toxic comments, hate speech, discriminative output, and violent output. We want a model to be able to safeguard all those harmful output. And also, this is not a sort of one-time process. It's an iterative process, right? As you can imagine, like any other machine learning process. So you don't want to just go straight to train your 100 billion parameter with 10 trillion token input. You want to start small with a smaller model, smaller data set, and tweak your all the hyperparameters you have in your model, and also evaluate your model every step along the way at every checkpoint to make sure you're doing it right, and then gradually scale it up to more data and to a bigger model. And I think another really important point I wanted to mention around model evaluation is that so all the sort of whatever it might be a loss for next token prediction or something more complicated metrics, all these metrics are just a proxy to what we really want the model to do, right? It's a really important point to keep in mind that if someone wants to build their own LLMs, you don't want to fixate it on one single metric or a small set of metrics because you may over-optimize those metrics, and so the LLM may end up not really working as you expected. I think LLM training is actually a really good example for Goodhart's law, which it says when a measure becomes a target, then it ceases to become a good measure. Right? So you really want to make sure that you are measuring the right things, and it's not a single metric, because LLM is a very complex system. Dive a little bit deeper into it. So the first two layers in the last slide is pre-training, and pre-training's goal is to create this base model. Again, crafting the right model architecture, data collection, these days typically means tens of trillions of tokens. It's probably going to just keep growing as we speak. And parsing, filtering is really important. You want to kind of, there's typically a lot of filtering going on in the pre-training data set, tokenization, and then gradually scale up your model training to the model size you're looking for. And another important thing you want to call out is that because the Mamba architecture, it has a unique advantage in handling long context window. So we put a lot of focus in the context expansion step, which after the majority of the training data set, probably is around 4K to 8K token, we also did a lot of work to have the model learn much larger context, so that model will perform well, for the ranges we want them to be, up to 256K in our case. So that's roughly the very high level pre-training. And then after pre-training, you have the base model. So now you want to do alignment, right? What is alignment? Again, we talked about earlier, alignment is a process we want to encode our human preferences and values into the model. This is a very simple example of alignment. For example, when we have the base model, let's say we feed this question to the model. This question is, if you can't see it, I'll read out to you. I need a list of 3 innovative ways to use peanut butter that go beyond sandwiches and salad dressing. By the way, I don't know who uses peanut butter for salad dressing. If you are, raise your hand, don't be shy. Number the items on a list using lowercase Roman numerals. So that's a question, right? Let's say we feed this question to the LLM, and the LLM came back with 2 answers. And this is pretty straightforward, whether it's a human evaluator or another LLM being the evaluator here, they can probably pretty easy to point out that the first answer is correct and the second is wrong because it didn't follow the instruction, which said you need to give me 3 things. This is pretty straightforward and not a lot of controversy here. But again, if we keep going down the path, what if the LLM gave these two answers, A and B down here? We can kind of make an argument and say answer A is better than answer B because it gives us more information, it's more helpful, more engaging. But really, it is a human preference. There's really nothing very wrong with answer B. And so this is where human preference come in. We say, hey, we prefer 1 because X, Y, Z. And this is a fairly simple question, but you can probably imagine there can be pretty vague cases where different human evaluators can give different preferences and will nudge the model in different directions. So again, I think in today's LLM development, sort of this alignment, data quality, and human annotation is a very, very active research, and it's something that everybody's sort of making a lot of effort. Yeah, so far, we briefly and very high level talk about pre-training and alignment, right? It's very, very oversimplified view of what's actually going on. If we sort of look beyond the basics, there are also a couple of things we'd love to kind of share about what we have been doing, and it might be interesting for you to hear. First thing is actually called ablations. If you remember anything from today's talk, or any takeaways from today's talk, I hope it's ablations, because it makes us all sound very smart. If you can remember this, I think you'll earn the bragging right to your colleagues. So ablation basically means that when we optimize, it's a methodology to optimize LLM hyperparameter. Right? There's many hyperparameters in when you train LLM, including how you sort of the data mix in your training data set, what you filter out, what not, what sort of tasks you want the model to learn, and as well as the model architecture. In this case, Mamba versus Transformer, what ratio do you want, sort of what is the right ratio for transformer layers in your model architecture? All of those are hyperparameters. There is also MOE ablation as well. How many number of experts, how do you, sort of what's the ratio, how many you want them to be activated, and all that load balancing, and how do you pick the right experts for the right job. So all of those are hyperparameters which you want to train, and the way to do this is through ablations. Basically, you keep some of the hyperparameters fixed, and then sweep through for the other hyperparameters. Just because there are too many hyperparameters, you can't. If you try to optimize them together, it will be just computationally impossible to do. So that's ablation. So basically, a way of doing hyperparameter optimization for LLMs. And also, like we talked about earlier, evals. What evals you do is super important, and how you do it is also very important. Your data set, the way sort of the human evaluators or LLM evaluators are giving rating the answer. Another also important thing is about compute. We all know that training LLM requires very, very large scale and expensive infrastructure setup that could often mean at least thousands of GPUs for several months. So synchronization between GPUs is very, very difficult. It's not a trivial task to do. And also, your training process could crash, and how do you sort of resume it? And also, their checkpoint saving when every checkpoint could be a few terabyte big, and how do you offload the checkpoint efficiently? Otherwise, it might be time consuming, or also adding on additional cost for the training process as well. And there's different type of parallelism to run, slicing the data, slicing your model to improve your compute efficiency. And all in all, on the compute side, the goal is to train your model with your infrastructure in a most efficient way. But all the hard work pays off. So eventually, the Jamba model came out doing really, really well. It performs really well in terms of output quality. It has very, very good throughput, compared 3x to the model in a similar size class. And also, it has a very, very long context window, 256K, for longest in its size class. A bit summary and highlight to wrap up sort of the Jamba's results. So it is a Mamba plus Transformer MOE architecture, and it have 52 billion parameters in total and 12 billion parameter active because of MOE, and it really outperforms other models in similar size class, 3x throughput, and 256K maximum context window, basically how many words you can fit into the prompt. And if you wanted to sort of really be efficient on your hardware, you can fit 140K on a single GPU with the right quantization approach. Yeah, so where do we go kind of from here, right? So I think we've all been interacting with different LLMs quite often, and making discrete and individual separate API calls to different models often is not going to help solve your business problem directly. And we believe we need a more robust AI systems going in the future. And this actually, I think, aligns with Matei's and overall the keynote messaging from this conference pretty well. A couple of things, I think you probably heard already, but some things we've been actively working on is how can we sort of leverage multiple models, often specialized and smaller models, in the pipeline to do different tasks. So you have a system that can help you really break down a complex task and solve them for you. And how can we have a system that can have ability to access different tools, external API calling, function calling, code execution, web search, whatever, and also be able to connect with other technologies for data input and output. This is a kind of a preview, or I think this is something we're already been developing and we'll keep adding onto it, is as of now, at AI21 Labs, we are developing this AI systems called task-specific models. So the approach we're taking for now is that, so we take our foundation model and we run a lot of fine-tuning on it. Those fine-tunings are, there's also a lot of additional data curation and the pre-processing goes into it. Of course, because the team has a ton of experiences doing alignment, the fine-tuning technique is also very strong at the team. And we also want to build into pre- and post-processing steps. For example, if we're sort of doing some sort of agentic RAG workflow, you want the system to be able to extract answer properly from your chat history, for example, giving the context of the discussion. It may be a customer interaction where there are already a bunch of discussion before this particular question that the customer asks, and you wanted to incorporate those history of discussion plus whatever documentation and background of the company to make sure you actually construct the right question for the RAG workflow to use. And there's also a lot of post-processing. I think one thing we really emphasize on is that with a RAG workflow, for example, need to be very grounded, right? The hallucination need to be filtered out as much as they can, and will also help to provide better answer by generating multiple answers from different retrievals and combining them all in the same system behind a single API, so users have an easier experience of getting the right answer without having to build out this whole pipeline for themselves. We also have our own chunking model, by the way. The chunking model sort of dynamically based on the semantic meaning of the text and groups the text by different topics. So it's not a fixed length chunking like most times we're using. And also two more things I want to call out. With this AI systems, I think this is something we're doing already, but I believe there is a bigger demand in reduced demand on prompting, right? And we all know that to get the right answer from LLM, often you need to do a lot of prompt engineering. But really for today, prompt engineering is not a feature, right? It's more a bug, because you have to be very careful with the choice of your word, and the model can be very sensitive to very trivial word choices, which is not how we want to talk to another human being, right? So in this kind of systems, we build into a layer of abstraction, so users don't have to do prompt engineering, right? They just send, for example, a summarization task to the model. Only takes, taking your document. You don't have to describe your task anymore. You don't have to give instructions to the model. The model will be able to just take your input text and give you a summarization, right? So it also, in the same process, it eliminated the chances for jailbreaking, for prompt injection as well, right? So also we do a lot of work around model hardening to protect against this sort of malicious behavior as well. So all in all, we're doing a lot of work in building our AI systems, and there's more to come, but so far we have, I believe, 12 different task-specific models helping user to run different type of summarization, RAG, and many different text editing tasks as well. Feel free to go check it out. Yeah, last slide. I want to call out again, this Jamba foundation model is on Hugging Face. It's open sourced. And our Jamba foundation model instruct version is also on our SaaS, and along with all the other task-specific models we just mentioned. So feel free to go give it a try, especially if you have a long context window use cases. This could really hopefully help solve your problem. Awesome. We're right on time. We have 20 seconds left. All right, I think Databricks told me that there is a survey they ask you to do on the app. So if you don't give us 5 stars, we'll track you down. Thank you.